Hello everyone. In this tutorial, we are going to cover a topic, asymptotic notations. So this is the outline of our presentation. We will start from what is asymptotic notation, why asymptotic notation is important, types of asymptotic notations, properties of asymptotic notations, advantages and disadvantages of asymptotic notations. What is asymptotic notation? As we know that asymptotic notation is used to measure the growth rate of a function or of an algorithm, so that we can distinguish the algorithm into different complexity classes. Asymptotic notation is used to categorize algorithms into complexity classes such as polynomial time classes, exponential time classes or logarithmic time classes. Or we can say that asymptotic notations are mathematical tools to represent the time complexity of algorithms for asymptotic analysis. Why asymptotic notation is important? First one is algorithm analysis. For example, if a particular problem is given and to solve that particular problem, there are more than one different algorithms are available, then we have to analyze the algorithm so that we can find out the best one. So asymptotic notation is a very important method for analyzing algorithms and understanding their efficiency. This analysis is essential for selecting the most efficient algorithm for a given problem. But whenever we are going to analyze a particular algorithm, there are some factors are present which can influence the analysis of algorithm. So what are the factors? Number of steps present in an algorithm. If a user used maximum number of steps in an algorithm, then definitely the time complexity will be increased. So we have to very careful during design of our algorithm that we have to conclude the algorithm with a minimum number of steps. Next one is different operators used in an algorithm. For example, if a user solved a particular problem using addition operator and another user solved that problem using multiplication operator. So what happened? The time complexity will be minimum for the user who used addition operator and the time complexity will be maximum for the user who used multiplication operator. So we have to be very careful during the selection of operators. Processing speed of the machine. If the processing speed of the machine is very high, then the time complexity will be minimum. If the processing speed of the machine is very low, then the time complexity will be maximum. And the last one is input sequence provided by the user. If the input sequence provided by the user is maximum, then definitely the time complexity will be maximum. If the input sequence is minimum, then the time complexity will be minimum. So during an analysis of an algorithm, we have to focus on these points so that we can minimize the time complexity. Next parameter is algorithm comparison. So if a particular algorithm is given and we want to compare the algorithms with respect to best case, worst case or average case, then asymptotic notation plays a vital role. Asymptotic notation provides a standard way to compare the performance of different algorithms without being influenced by specific hardware or software details. Whenever we are going to compare the different algorithms, we don't consider the software or the hardware that used in the algorithm. So using asymptotic notation, you can easily compare the different algorithms. The next topic is predicting performance. So asymptotic notation allows us to predict how an algorithm will perform as input size become very large. So whenever the input sequence will be large, so what effect will be on the algorithm, that we can easily calculate using the asymptotic notation. Next one is algorithm design. So whenever an user is going to design an algorithm, he must have to focus on two things. One is efficiency and second one is functionality. So efficiency and functionality both are trade-offs. That means simultaneously we can't satisfy both the condition. So asymptotic notation help us so that we can take a decision about the trade-offs of efficiency and functionality. Types of asymptotic notations. So basically there are 5 types of asymptotic notations are present: big O notation, big omega notation, big theta notation, little o notation and little omega notation. During our presentation, we will cover the topic big O notation, big omega notation and big theta notation. So let's start with big O notation. So actually big O notation is used to find out the upper limit or upper bound of a given function or given algorithm. So big O notation represents the upper bound of the running time of an algorithm. So it is provide the worst case complexity of an algorithm, because big O notation deals with upper limit or upper bound so that we can relate it with worst case time complexity, because we know the worst case time complexity deals with the maximum value. For this reason we can correlate the things. So the definition is that the function f of n is big O of g of n should be written as f of n is equals to big O of g of n if there exist two positive constants c and n naught such that f of n less than equals to c into g of n for all n greater than equals to n naught. That means there are two different functions, one is f of n and second one is g of n. So f of n is equals to big O of g of n whenever the value of f of n will be less than or equals to c into g of n. In the graphical representation, there are two lines are present, one is f of n and second one is c into g of n. But you have to focus on the point n naught. That means after the point n naught, the value of f of n is always less than c into g of n. But before that, that means from point number 1 to n naught minus 1, the value of f of n sometimes may greater than c into g of n, or sometimes it will be less than from c into g of n. But after we have calculated the value of n naught, the value of f of n will always less than c into g of n. For example, f of n is given, that is 2n square plus 3n plus 5, and we have to prove that this f of n is equals to big O of n square. Or indirectly, this type of question will be given, calculate the upper limit of the above function. Whenever we are dealing with upper limit, that means indirectly we are dealing with big O notation. So this type of question will be given to you and you have to prove that this function will satisfy the big O notation, or you have to calculate the upper limit of the given function. So the solution is given, how we can prove that f of n is equals to big O of n square. So as we know that the big O notation, the condition is that we have to check the value of f of n is less than equals to c into g of n for all n greater than equals to n naught. That means we have to find out the value of n naught so that we can prove with the value of n that after this point the value of f of n will be less than equals to c into g of n. So the equation we can define as 2n square plus 3n plus 5 will be less than equals to 2n square plus 3n plus n. So mathematically this equation will be possible when we start the value of n after 5 or greater than equals to 5. That means whenever the value of n will start from 5, we can satisfy this condition. So n is greater than equals to 5. If we compare this function with n greater than equals to n naught, then n naught value will be 5. So we can rewrite the sentence, 2n square plus 3n plus 5 will be less than equals to 2n square plus 4n. But our prime objective is to bring this function into c into g of n form. So further we can rewrite this equation as 2n square plus 4n will be less than equals to 2n square plus n square. So mathematically it will be true when we substitute n square with greater than equals to 4n. That means if we cancel n from LHS and RHS, then the value will be n greater than equals to 4. If we compare this value with n greater than equals to n naught, then we will obtain n naught equals to 4. That means if we start from n equals to 4, then 2n square plus 4n will always less than or equals to 2n square plus n square. So we can simplify the equation that 2n square plus 4n will be less than equals to 3n square. That means this satisfy the condition of c into g of n. Okay. So we conclude that the function f of n is equals to 2n square plus 3n plus 5, which will always be less than or equal to g of n, that is n square, when we start the value of n with 4 or 5. That means this n naught we can set that it will be 4, or for the upper limit we can start the value of n naught at 5. So we can prove that this function f of n, that is 2n square plus 3n plus 5, is big O of n square when the value of n naught is equals to 4 or 5. But here the question arises that is this the upper limit of that particular function f of n? We can also solve this problem. 2n square plus 3n plus 5 is equals to big O of nq. That means if we set that order of nq, then this equation will be also true. Also this function f of n is true for n to the power 4, and also it is true for 2 to the power n. That means here this function f of n, the upper limit may be n square, may be nq, may be n to the power 4, or it may be 2 to the power n. So here we don't know the exact limit, upper limit of this given function, because it is true for n square, it is true for n cube, it is true for n to the power 4, and also it is true for 2 to the power n. So big O notation is used whenever we don't know the exact upper limit of that particular function. In that case, we can use big O notation. But which one is useful? The useful is the closest one, that means order of n square. So order of n square is true, n cube is true, 2 to the power n is true, but we have to select the closer one, that is n square. So whenever we don't know the exact limit or the exact upper limit of that particular function, then we can use the big O notation. Now big omega notation. So big omega notation is used to find out the lower limit or lower bound of a given function. Omega notation represent the lower bound of the running time of an algorithm. Because it is dealing with lower bound or lower limit, that means it will dealing with the less value. So we can correlate the things with the best case complexity of an algorithm. Definition. The function f of n is big omega of g of n, should be written as f of n is equals to omega of g of n if there exist two positive constant c and n naught, such that f of n is greater than equals to c into g of n for all n greater than equals to n naught. In the graphical representation, here f of n and c into g of n, two lines are present, but you have to carefully observe that after the value of n naught, the value of f of n is always greater than c into g of n. But before that, from 1 to n naught minus 1, the value of f of n sometimes may be less than c into g of n, or it may be sometimes greater than c into g of n. But if once we set the value of n naught, after that the value of f of n will always greater than c into g of n. For example, if the f of n is equals to 2n square plus 3n plus 5, in the previous example we have already defined it for big O notation. Using the same process, we can set that this condition is true when the omega value is n square. It also true for omega of n, it is also true for omega of square root n, and it is also true for omega of log n. That means we don't know the clear exact lower limit of this particular function. So whenever we don't know the exact lower limit, we can use the omega notation, because for this particular function n square may be the lower limit, n may be the lower limit, square root n may be the lower limit, or it may be the log n. So we don't know the exact lower limit of this particular function. So in that case, we can use the omega notation. Big theta notation. So basically big theta notation is used for average case complexity analysis, because it present in between big O and omega notation. So theta notation enclose the function from above and below. Since it represents the upper and the lower bound of the running time of an algorithm, it is used for the analyzing the average case complexity of an algorithm. So the definition is that the function f of n is big theta of g of n, written as f of n is equals to theta of g of n if there exist three positive constants c1, c2 and n naught, such that c1 into g of n will be less than equals to c2 into g of n for all n greater than equals to n naught. This is the graphical representation of theta notation. Here you can observe that the line f of n is present in between c1 into g of n and c2 into g of n. If we consider the line f of n and c1 into g of n, both these lines satisfy the omega notation, and the line c2 into g of n and f of n satisfy the big O notation. As we have already discussed that big O notation and omega notation, they are used for the specific reason. whenever big O notation is used for the upper limit and omega notation is used for the lower limit. So theta notation will be present in between big O notation and omega notation. Once we calculate the value of f of n, then after the value or the function f of n will lies in between c1 into g of n or c2 into g of n. But before that, sometimes f of n may be greater than c1 into g of n, or it may be greater than c2 into g of n, or sometimes it may be less than c1 into g of n or c2 into g of n. But once we set the value of n naught, then after f of n will always lies in between c1 into g of n and c2 into g of n. For example, we can say that if the function f of n is equals to 2n plus 5, and we have said that this is theta of n, that means the output of this asymptotic notation of theta is defined as theta of n. So it is true, but if the function 2n plus 5 and we are going to set the value of theta is n square, then it will be false. Also for square root of n, it will be false. Theta means when we know the exact value of this particular function, then we can use the theta notation. So theta notation means the exact value. If the value is n, then we can't set n square and square root of n. We can't set the upper limit and we can't set the lower limit, because theta deals with the exact value. For this reason, for this example 1, the I value will be true, and these other two equations, that is 2i and 3i, will be false for this particular notation. Now properties of asymptotic notations. So there are different type of properties are present in the asymptotic notation, and we can use these properties to solve different type of problems. The first one is the general properties. If f of n is big O of g of n, then a into f of n is also big O of g of n, where a is a constant. That means if a function is given and that function is bounded by big O of g of n, then if we multiply a constant value into the f of n, then the output will always be the order of g of n. For example, if f of n is equals to 2n square plus 5 is order of n square, that means here the value of f of n is 2n square plus 5 and the value of g of n is n square. And if we multiply the constant value 7 with f of n, then the output will be 14n square plus 35, and the growth rate of that particular function after multiplying of 7 is also a quadratic equation, that is order of n square. So we have to remember that this general property will be followed by big O, omega and theta notation. All three notations will satisfy this condition or this property. Next property is transitive properties. So if f of n is big O of g of n and g of n is big O of h of n, then we can conclude that the function f of n is big O of h of n. That means if a function is given and that function is bounded by g of big O of g of n and also g of n is bounded by big O of h of n, then we can conclude that the initial function f of n must be bounded by big O of h of n. For example, we can say that if the value of f of n is n, that means growth rate of this particular function is a linear, and the growth rate of the second equation, that is g of n, is equals to n square, that means the growth rate is in the quadratic manner, and the third function h of n is equals to n cube, that means the growth rate of this particular function h of n is in cubic. Here we can observe that the growth rate of the three different functions are different, where f of n growth rate is linear, g of n's growth rate is quadratic and h of n's growth rate is cubic. But here, as per the transitive property, we can define that n is order of big O of n square, because f of n is big O of g of n. So the value of f of n is n, so n is big O of n square and g of n is big O of h of n. That means the value of g of n is n square, so we can rewrite that n square is big O of n cube, so that we can conclude that f of n is equals to big O of h of n. So what is the value of f of n? F of n is n, and what is the value of h of n? H of n is n cube. So we can conclude that n is big O of order of n cube. Similarly, these transitive properties will followed by or satisfied by theta notation and omega notation. That means we have to remember that big O, omega and theta, all these notations satisfy transitive properties. Next one is symmetric properties. If the function f of n is given and f of n is bounded by theta of g of n, then g of n is also bounded by theta of f of n. That means if there are two functions are given, f of n and g of n, and that function f of n is bounded by theta of g of n, then we can conclude that the function g of n will also bounded by theta of f of n. For example, if f of n is equals to n square and g of n is equals to n square, then we can conclude that f of n is equals to theta of n square and also g of n is equals to theta of n square. This property only satisfies the theta notation. That means big O notation and omega notation does not satisfy the symmetric properties. We have to remember this theta notation only satisfies the symmetric property. Next one is transpose symmetric properties. So if there are two functions are given, f of n is big O of g of n, that means it is bounded by big O notation, then the function g of n is omega of f of n. That means if f of n is bounded by big O of g of n, then we can conclude that the function g of n will also bounded by the omega of f of n. For example, if f of n is equals to n and g of n is equals to n square, that means the growth rate of the function f of n is a linear and the growth rate of the g of n is in quadratic. Then we can conclude that n is big O of n square and n square is omega of n. So here if we compare n is big O of n square, whenever we are going to describe the big O notation, that means the function f of n will always less than equals to c into g of n. So here the value of f of n is n and the value of g of n is n square. So always n will be less than n square. So it satisfies the property of big O notation. And we can conclude that n square is omega of n. So whenever we are dealing with omega notation, we know that the condition f of n is greater than equals to c into g of n. So here the value of f of n is n square and the value of g of n is n. So we can conclude that n square is greater than equals to 1. So both the conditions are satisfied, but we have to remember that this property only satisfied by big O and omega notation. Theta does not satisfy the condition because we know that theta is used for the exact value. But here we are dealing with uppercase and lowercase. So big O and omega, these two notations will satisfy this transpose symmetric properties. So advantages of asymptotic notation. So there are some advantages present and also some disadvantages are present. So first of all, we will describe the advantages. So the first advantage is asymptotic analysis provide a high level understanding of how an algorithm perform with respect to the input size. If a particular algorithm is present and we increase the input size, then we have to check that with respect to the input size performance, how the algorithm behave. That means what is the performance of the algorithm if we increase the input size. So using asymptotic notation, we can easily calculate the things. The second advantage is that it is a useful tool for comparing the efficiency of different algorithms and selecting the best one for a specific problem. So whenever we are going to select the best algorithm from the set of algorithms, we will use the asymptotic notations so that we can pick the best one from the given set of algorithms. It helps in predicting how an algorithm will perform on large input size, which is essential for real world application. So basically algorithm, whenever we are using these algorithms in the real life scenario or real world application, we have to calculate what is the performance of the algorithm if we increase the number of input size. So also using asymptotic notations, we can monitor the values. And the last advantage is that asymptotic analysis is relatively easy to perform and requires only basic mathematical skills. We know that in mathematically 2n square plus 3n plus 5 is not equal with 2n square. The growth rate of that 2n square plus 3n plus 5 is in also quadratic and the growth rate of 2n square is also quadratic. That means asymptotically they are equal, but mathematically they are not equal. So whenever we are going to represent the function with the asymptotic notation, we don't require the mathematical skills because here mathematically they are not equal, but asymptotically the growth rate wise they are equal. We can say that they are belongs to a particular classes. okay, but mathematically they are not equal, and there is also no mathematical skill is required to identify the asymptotic notation analysis. Disadvantage of asymptotic notation. So we have already mentioned some advantages. Now we will focus on the disadvantages of asymptotic notations. So first disadvantage is that asymptotic analysis does not provide an accurate running time or space uses of an algorithm. So it does not provide the accurate value, exact value, it provides the asymptotic value. So sometimes if we want to calculate the exact value or accurate running time of an algorithm, then in that particular cases asymptotic notation is not suitable, because asymptotic notations provide the asymptotic value. It does not provide the accurate value or the exact running time value of any specific algorithm. The second point is that it assumes that the input size is the only factor that affects algorithm performance, which is not always the case in practice. So apart from this input size, there are so many other factors are present which can influence the time complexity. As we have already discussed that it depends upon the performance speed of the machine, it depends upon the number of operators used by the user, it depends upon the number of input provided by the user. So there are so many factors are present, but asymptotic notation is only consider the number of inputs that is provided by the user. So this is the second disadvantage of asymptotic notation. The third disadvantage is that asymptotic analysis can sometimes be misleading, as two algorithms which are the same asymptotic complexity may have different actual running time or space uses. So whenever we will calculate the actual running time and the space case complexity, that means there are two factors by using that we can calculate the complexity performance of an algorithm, that is time complexity, and second one is space complexity. So sometimes it observed that it provide the two different algorithms having the same time complexity, but actually they are not the same time complexity. Asymptotically they may equal, but in the real value they are not equal. So sometimes it provide the misleading values. And the last disadvantage is that it is not always straightforward to determine the best asymptotic complexity for an algorithm, as there may be a trade-off between time and space complexity. As we know that time and space are trade-off. Simultaneously, we can't design an algorithm that can satisfy both the conditions. That means the algorithm which can provide the best result using minimum time and minimum space, that is not possible, because both the values are trade-offs. So this is the basic disadvantage of asymptotic notation, and we conclude that asymptotic notations are very useful when we are going to compare the different algorithms, or when we are going to analyze the different algorithms. Asymptotic notations are the best tools that is available, so that you can compare and analyze the best algorithm. So apart from these three notations, there are two more notations are present, that is little o notation and little omega notation. So little o and little omega notation, there are some specific conditions are given, and if the condition is satisfied, then we can say that the particular function satisfy the little o notation, and also if a specific function is given and that function satisfies some conditions, then we can say that it satisfies the little omega notation. So what is little o notation? So definition is that the function f of n is little o of g of n if it satisfies the following condition: limit n tends to infinity, f of n divided by g of n is equals to 0. That means if a function is given, that is f of n, and another function is given g of n, if we calculate the limit value and f of n of g of n and the result is 0, then we can conclude that that particular function satisfies the little o notation. Apart from 0, if any other value achieved, then we can't conclude that that particular function f of n satisfies the little o notation. So in this particular notation, we have to check the condition. If the condition is satisfied, then we conclude that this particular function satisfies the little o notation. If the condition is not satisfied, then we can conclude that that particular function does not satisfy the little o notation. We have to remember that the little o notation, that limit n tends to infinity, f of n divided by g of n is equals to 0. That is the condition or property of little o notation. Little omega notation. So the definition is the function f of n is little omega of g of n if it satisfies the condition limit n tends to infinity, f of n divided by g of n is equals to infinity, or limit n tends to infinity, g of n divided by f of n is equals to 0. That means if we put the value of f of n and g of n into the limit function, if the value is infinity, then we can conclude that the particular function satisfy the little omega notation, or we can reverse the function. That means limit n tends to infinity, g of n divided by f of n. If the output is 0, then we can conclude that that particular function satisfy the little omega notation. So basically little o and little omega notation, they are dealing with the specific functions. The function is given, the property is given. If that function satisfy that condition, we can conclude that particular function belong to little o notation. If the condition is not satisfy that, we can conclude that the function is not satisfy the condition. So these are the asymptotic notation, and using that asymptotic notation we can find out the different type of notations and where we can apply the notations. So we have to remember that when we don't know the exact upper limit, that means suppose a linear function is given, for the upper limit may be n square, n cube, n to the power 4 or up to 2 to the power n. So here in that we can use the big O notation. Whenever we don't know the exact lower limit, if a linear function is given, then the lower limit will be the n square root n log n. So we don't know the exact lower limit. So in that case theta will be used. And whenever we are dealing with the exact value, basically in graph data structure, we are using the theta notation to represent the complexity, because theta means the exact value we know and the exact running time, growth time we know, and we are going to represent. So these are the asymptotic notations, and using these asymptotic notations we can measure the growth rate of any algorithm or any problem that is given to us. Thank you.